So hello everyone, I am Divyansh MSc second year student, physics of course. So before I start, how many of you are from physics department? And how many of you are from any other department, like electrical, which department? Aerospace, etc. Do you all know quantum mechanics? How many of people know how to solve 1D infinite well problem? Like harmonic oscillator. You guys don't know harmonic oscillator? Okay. So I'm assuming you know basic quantum mechanics, like Schrodinger equation and everything. So our topic is flipping spins in quantum world and Ising model. So what basically it is just a mechanism to explain origin of magnetism. So like how magnetism come to play, how field theory and other aspect explains magnetism, and what is Curie temperature and all those things. So it is very interesting thing. So let's begin. So as we all know, like spins are up and down and up and down. So we are talking here about a material which has a fixed lattice, like particles are the lattice sides are bound, and on each lattice side there are electrons, mostly free electrons. Like if there are no free electrons, we are not talking about magnetism here. So we are talking about electrons which can have spin up and down, up and down. So all these are lattice sides. So this is a 2D map. So like it is spin up, spin down, spin up, spin down. It is all random at this point. So when we talk about magnetism, we talk about how the material is responding to a magnetic field, or how it is interacting with metal, etc. So it all comes from this alignment of spins, how these spins are aligning, how spins are interacting within themselves. So it is a very interesting thing to see how this arrangement of spin and how this alignment will evolve as we increase or decrease temperature and all sorts of things. So before I start about spin and all, I just want to talk about harmonic oscillator first. So we all know classical harmonic oscillator, right? P square plus x. So in quantum world we can write Hamiltonian as kinetic energy plus potential energy. So this is a Hamiltonian for harmonic oscillator. So when we solve this harmonic oscillator, so this is our potential curve. So this is, I am plotting as a psi, and this is x. So we get solution of harmonic oscillators as this kinds of solution. First excited state, second excited state, typically as like n equals to 1, 2, 3, 4 and so on and so forth. Like the calculation of showing all this is intense. I will skip that, but we can write all this harmonic oscillator in another way in which most physics is done. I will define something as A dagger as pi cap minus x and A as ip plus x. So when we multiply, we get p square plus root of m omega square. So we just normalize it. So I will do this, and m omega square upon 2. So I'm defining two new terms, A dagger and A. A dagger as ip upon root 2m minus k, this term, and A as this term. So when we define states A dagger and A, we can write this harmonic Hamiltonian in a very nice and compact way, and it actually show very beautiful thing, because when we act this A dagger operator on ground state, n equals to, let's say, 1. So we actually get a second excited state. Sorry, when we act this on a first excited state, we get a second excited state, and when we act A on this, let's say, first excited state, we get a ground state. So this is a very interesting way to write defining harmonic oscillator in A and A dagger terms. So A dagger basically means we are jumping from ground to first to second to third, and an A means just lowering this term. So we're gonna use this A dagger A term. So we also about the commutation relation. So we all know xp is IH cross, and putting H as a 1. So we get a commutation relation of EI AJ dagger as delta IJ and EI AJ equals to 0. So basically we all know electrons are fermions, and fermions obey anti-commutation relation. Do people know about commutation and anti-commutation relation here? Is there anybody who do not know? You don't know anti-commutation commutation relation. So commutation relation basically means when I write A B, it means A B minus B A, and anti-commutation relation means if I writing A B minus equals to A B plus B A. So all the bosonic particles, fields, etc. Follow this commutation relation, and fermionic particles follow anti-commutation relation. So when I say AI AJ dagger, it means AI AJ dagger minus AJ dagger AI. So it basically for bosonic it turns out to be delta Ij, and for fermions it follow anti-commutation relation. So Ci Cj dagger is equals to delta Ij. So as you can see, like for bosons, they can occupy any number of in one state any number of particles can occupy it, and for fermions it follows Pauli exclusion principle. So why do we need this? So basically when we write interaction Hamiltonian for spin chain, we want to solve it. So we cannot solve it. So I will just show the how many of people have heard about tight bonding model? How many people who haven't heard about tight binding model? Okay, so what is tight binding model? So basically, so we have our lattice sites here. And we have some electrons here. And they each occupies some kind of spin. Okay, so we want to like write a mechanism to explain the interaction among the spin. Okay, so like this spin up and spin down will interact, and this spin up, spin down and interact, and so on and so forth. So to explain this interaction, we introduce something as a tight binding model. So what is this term? So I will say these sides something I plus 1, I plus 2, and this is I minus 1, I minus 2, so on and so forth. So how I am defining this interaction term among this is, let's say any two spins are interacting, so Si, Sj, and some coefficient, and summing over all Si and Sj. So this is how I am defining the interaction between the spins. So this is interaction, this is a coefficient or whatever you say, scaling factor, and as this is let's say xx plus j Si j plus j. So this is like x as like spin is has 3 directions, so all 3 directions are interacting like this. We are not considering any cross term or anything else. So how physics works is to solve the most simple equation. I cannot solve this, nobody can solve this. Okay, I want to write this something as a which is soluble. So I am ignoring any interaction term which is more than one unit length. So I am just talking about interaction of nearest neighbor term. Any two spin which are far apart, I am considering those interaction to be 0. And in this, so if we just ignore all the terms in which interaction is far. So we just get this Hamiltonian, like n plus 1 and n plus 1 and n plus 1. So far, anybody have any questions? It's all smooth right now. So this is a x, z model. So x term, y term and z term. So these are Pauli matrices. So spin is defined by a Pauli matrices, and h cut by 2 is normalized. So there are many kind of models we can talk about. One model which we gonna study is XX model. So that is xj and jx and jy equals to say same j, and jz equals to 0. So we are ignoring this jth z component. We can do it, but we will not do it. So other are like all this Ising model, etc. So to find magnetism, all we need to do is find solution to this Hamiltonian, and this will explain all the properties of magnetism. So that is what basically we are trying to do. But problem is that to find solutions for Hamiltonian, we need all we need to do is find the eigenstates and eigenvalues, and for that we need to diagonalize this Hamiltonian. But you can see the number n here. N can be like 1000, 10,000, whatever, and these are like 2 by 2 matrices, and this is another 2 by 2, another 2 by 2, 2 by 2. So multiplying these matrices and adding thousands of matrices, it is not something we can do, right? Like diagonalizing this is a nightmare. So to solve this problem of diagonalizing, what we will try to do is convert this Hamiltonian into bosonic Hamiltonian. Why we are doing it? Because it is very easy to diagonalize when a Hamiltonian is bosonic or something like that. And there is so when we try to convert this into bosonic, first what we try to do is convert this into something like something very trivial. So this is 2 by 2 matrix. We don't want to solve 2 by 2 matrix. So that's why I will now compare two terms. So before that, we can define this S plus and S minus. This is spin up and spin down. So all it do is basically flip the spin. So you can prove it, but it will be very tidy. So those who don't understand this now, just assume it to be true. And if they have any question regarding that, they can ask me right now. But yeah, so what basically S plus do is just increase the spin, change the spin to up. So acting on spin up will be 0, and Sn minus will do decrease the spin, and acting on the spin down it will be 0. So when we try to substitute Sx and Sy into the previous Hamiltonian, this in this Hamiltonian we will get this new Hamiltonian. So So in this new Hamiltonian we have term Sn plus S minus n plus 1, Sn minus n S plus n plus 1. So this something we can which we can transform into something very doable. So I will right now try to correlate few things. So this is our potential value. So this is state 1 and this is state 0. So whatever, and this is spin up and spin down of any particle, let's say electron. So as we knew, like a dagger, we go up the ladder if we apply a dagger, and we go down the ladder if we apply on the tops on the ladder. So I am saying if state is in a zero state, like ground state, there are no particles. If the state is in the state of 1, there is one particle. If state in excited state 2, so there are 2 particles, 3 particles, 4 particles, and so on and so forth. And so basically what a dagger doing, if I am defining this to be like 0 particle, 1 particle, 2 particle, 3 particle, so what a dagger is doing is creating new particle every time I am applying it on a state. So what basically it means is adding a new particle in this system as I apply a dagger. So, and Sn means like flipping spin, like if it is spin down, it is flipping up to spin 1. So what I will try to claim here is spin up is equivalent to state 1, spin down is equivalent to ground state. This is something correlation I will try to make. Spin up equals to 1 and spin down equals to 0. So when I make this correlation, the Sn plus becomes Cn dagger, Sn minus becomes Cn annihilation operator, and now we need to write a number operator. So as we all know, the eigenvalues of this Hamiltonian is n into n plus 1 divided by 2. So if it is in a ground state, n will be 0. If it is in a first excited state, n will be 1, so on and so forth. So if we try to see what the value it will give, so it will be just n. So this is just an eigen energy, and we are correlating energy to the number of particle, and correlation to that is Zn. We don't need to prove this won't be needful, but yeah, the commutation relation it becomes here is Cn dagger equals to 1, and this is Sn plus and Sn minus dagger equals to 1. So we are able to establish a correlation between the fermions and spin. So now we will try to write that Hamiltonian in this fashion. So So if we're gonna write this as a Cn, so this is plus, right? Cn dagger, this will be Cn plus 1, this will be Cn, and this will be Cn plus 1 dagger. So it will just plus multiply is j by 2, there was summation over n, summation over n. So this is the Hamiltonian in terms of creation and annihilation operators. So but it has one problem. One problem is that any two electron will if we exchange them, we will get a minus sign. So that means those electrons anti-commute. So the problem in this is this Cn and any two different sides, they do not commute. So to make them commute, we need to write something. We need to transform this Sn plus and Sn minus such way that any two sides also commute. So to do that, we define Sn plus and Sn minus in a new fashion. So what this is telling, this Cj dagger will number at that jth side, and this is just an exponent. So all it is trying to say is number of particles before the nth side, and same here. So it is just trying to say number of particles before side. So let's say it is a lattice site. We got an electron here, we got an electron here, we got an electron here, spin up, it is spin down, spin down, spin down. So we are talking about this side. So all that tell is what will Cj dagger Cj will give. Here it will give 1, here it will give 0, here it will give 1, it will 0, 1. So adding 1, 1, 1, so summation of Cj dagger will give 3. So and so all these are integers. So 1, 2, 3, 4, 5, 6, and I, pi, n. All these are integers. So I pi n will be like 1, 2, 3, 4. So it will be just 1, minus 1, 1, minus 1, 1, minus 1, 1, minus 1. So all it will tell is the parity of spins before the jth side. Okay, it is just telling the how many ups and downs are there before the jth side, the parity of it is. So we multiply, this is a parity operator, we say parity operator, parity operator. So when we multiply this, we get a so if we multiply Sn plus and Sn minus, so all these things will eventually cancel out, and actually you can show this. Wait, I'm missing something. I haven't wrote the explanation here. I forgot to add the slide where the transform Hamiltonian is. So when we add those parity sides, the Hamiltonian will just become summation of let's say C, we are defining Newton, right? So like alpha dagger J alpha. So that is a bit lengthy calculation. I have done it. I forgot to add the slide, my mistake. So when we substitute this new Sn and Sn plus, things magically cancel out and we just get a one simple Hamiltonian, which is this. This is also known as, like, famously a tight binding model. Like if you take condensed matter too, like this is tight binding model which you will learn. So now we got a Hamiltonian of all the spins interacting with each other. So now we need to find how the magnetism is arising and how it is gonna change with temperature. So before that, what is important to know is sign of this J. Is J positive, negative, or something else, because that matters. So here I have written plus J. So what is J? J is a coefficient of two spins interacting. So let's suppose we go on two different sides. So this side and this side, and one case will be this and this. So here the net spin is 0, here net spin is plus 1. So like half and half and minus half and half. So how do I know is this is favorable or this is favorable? So the way to know is when we write combined spin wave function for both the spin, it is singlet and triplet. Have you heard about singlet and triplets? How many of you haven't heard about singlet and triplet? You and so basically it is writing a combined wave function of two spins. So we are trying to write these two spins combined. So what are the possible ways? So this is like spin up, spin down, and spin up, spin down plus spin down, spin up. Another way is spin down minus spin down, spin up. So these are four possible ways to write the combined wave function of spin. So in this, the both spin are up, in this both spin are down. In this both case you see up and down and up and down, sorry, up and down and down and up, but we need to preserve symmetry and anti-symmetry of the particle. So when we exchange the particle, we want it to be either symmetric or anti-symmetric. So in this, writing this will be alone will not make sense, because when we exchange two particles, it is a different wave function. So this is a symmetric. When you exchange this two, you still again get this, and when you exchange this two, you get a minus sign here. So when this symmetric, this thing is favored, the J will get a positive sign, and when this thing is favored, J will get a negative sign. What it means is, when in a lattice, when two on two lattice sides, when the both spin are up, the energy lower, and if it favors this things, when both spin are opposite, it energy is lower. So this is how you get a sign for J. So that was sign of J was explained. I don't think we have time to explain interacting Hamiltonian, so I'm gonna skip that. So we got our Hamiltonian to be H equals to summation of Cj Magras Cj. So this we got this Hamiltonian. Now how the statistics of all the spins works. So we have a Hamiltonian. How many of you have done a statistical course in physics department? Only few. You guys haven't done this statistical. Okay. So basically, when they are like a very large number of particles, so the mechanics of those particles are driven by something called a partition function. So how partition function is defined is exponential minus beta h for non-interacting. What it basically means is when you have large number of particles, the more randomness this particle system have, the more it is favored. So if I say I am talking about spin, so more the spread of spin down, spin up, spin down, so more randomly all the spins are spread, more it is favored, and so the entropy is high when the randomness is high. So to explain this thing, we have a mechanism called partition function Z. So what it basically tells is exponential minus beta of Hamiltonian, and Hamiltonian is like what is governing the equations or like behavior of the particles. So beta is nothing but 1 upon kBt. kBt is Boltzmann constant. So deriving Z is not the scope of this talk, and it will be very lengthy. So I'll just make it very short here. So Z equals to e power minus beta h. So what this partition function tells is, this is the energy. So it will be basically minus h upon kBt. When temperature is very high, then more randomness and interaction is less, it dictates less, and when temperature is very low, it tells like more interaction and less randomness. So we got our Hamiltonian, that to be J Cj dagger Cj. So when these are just few terms from like partition function, free energy, magnetism, susceptibility. So I haven't written it. So J is basically that. So if we compare our Hamiltonian with this, so J equals to KBT, and the KB becomes T becomes J by KB. So when this temperature is very, very high than KB, the more randomness you will see in a lattice. So more spin will be randomly spread out, like up and down, it will be very random. And when the temperature is very low, so it will favor more and more alignment of the spins. So spin will try to align more and more and more. So have you done experiment in lab of finding Curie temperature or paramagnetic and ferromagnetic behavior of lattice? No. So you will do it if you are a physics department in some point of time or other. So what basically it says, what paramagnetism is, spins are randomly oriented, but when you apply magnetic field, they will try to orient themselves. And what ferromagnetism is, irrespective of magnetic field, all the spins are aligned towards certain direction. So you get a net spin without an external magnetic field. So when temperature is lower than this critical temperature, so you will see much more magnetism here, and when temperature is higher than critical temperature, you will see much less magnetism here. So it goes basically something like this. So it's just say that. So when temperature is much less than that critical temperature, so you will see more magnetism, and when it is higher, then you will see less magnetism. So you all know in paramagnetic susceptibility goes as 1 by T, right? So it comes from here only, like this this minus H upon KBT. So higher the temperature, more randomness it will have, so it will try to align more randomly irrespective of magnetic field applied or not applied. So higher the temperature, it is harder and harder to align the spin together. So the susceptibility decreases as you keep on increasing the temperature. So this is all about magnetism. Between this Tc is called Curie temperature given by Curie. So this is all these are some references which you can look up to. The quantum Ising model for beginners and this statistics. So we have tried to see the concept of ladder operator, 1D spin, Jordan-Wigner transformation. This was a Jordan-Wigner transformation in which we included parity of the spins and the turning complex interacting spin into non-interacting fermions. So here, why I'm saying non-interacting, because in this Hamiltonian, this is completely, in each term it is completely dependent on one side. Like you don't see J or any other term other than J. So it is a non-interacting term, but whereas in a previous Hamiltonian, it was n into n plus 1. So there are two terms, so it is interacting. So that's how I'm saying non-interacting. And this is followed by again partition function and thermodynamic physics versus paramagnetism and ferromagnetism and like Curie temperature. That's it. So if anybody of you have any questions? No one? And thank you. That's it.